Welcome back, and thank you for tuning in to my first episode of my new training series. A lot has changed since the last content I posted, and for the better. We are now officially Service Tech Heating and Cooling, our very own company. To my followers and subscribers out there, I thank you so much for your support. In my neck of the woods, winter's upon us. Cold fronts mysteriously looming around the foreseeable future in just a couple days. That means a lot of service calls are going to be coming in from no heat. If you can make it to the end of my video, I'm going to go over top 5 causes that I typically see for no heat and how I test for them and how I fix them. Before we can really get into any troubleshooting, we're going to have to understand some basic things, and that's what this first video is about. It's all about some basic things on the control circuit that governs an 80% furnace. Let's navigate these waters together. So today's content is the first video in probably a series of them, and only on the control circuit. Okay, we're going to kind of break things down to baby step our way through them. Looking at the picture above us, I have a typical setup for an 80% furnace. These are the safeties that are in that control circuit, and this is really kind of how it works. In a normal furnace situation, my flame is on, everything's running great. I can use my hopscotching method. I can plant one of my leads down here at the ground connection, any good ground that I can find, and use my free hand with the other side of my lead, and I can touch one of these spades. Every dot on my map up here is a spade coming in and out of one of these safety switches. Our first switch on my list is the pressure switch, and you really need a manometer to test this pressure switch to see if it's lying or not. If you prove through your hopscotching method that you have 24 volts going into the pressure switch, but you don't have it leaving it, we have an open switch. The highway's open. There is no path, right? No beep. Beep or no beep. Beep meaning there is a road there. That switch is indeed closed. The circuit is a closed circuit. No beep meaning there is no continuity. There is no path. There is no circuit. You shall not pass. The control circuit, while I'm thinking about, is a beautiful example of a series circuit versus something like a parallel circuit, how we see most of our motors being ran into things. And so series circuits are fairly easy to navigate, especially using the hopscotch method. Let's go back to that pressure switch. Every pressure switch in every furnace is going to be a little bit different, and the great news is what it's rated for is right on the pressure switch. When those pressures are met, that switch closes. Well, how do you prove if that switch is lying or if it's telling the truth? Is it really not meeting those pressures, or is it not meeting those pressures and it's not opening? So, do you really have a problem, or do you have a bad pressure switch? So using a manometer, we can run our tubing in line, and when the induced draft motor turns on, which creates that suction that's being read by the pressure switch, we can see it right there in digital form, what those real numbers look like. And one of two things is going to be happening. You're either not getting the pressures that you need, and that's going to be for a reason. Could be a bird in the flue pipe. There could be obstruction in there, jacked up blower. There's a bunch of different things could be reasons on why you're not achieving it. But say that you're proving it. You're seeing that the pressures are being met, but that switch still isn't closing like it's supposed to. It's a bad pressure switch. We didn't guess. We didn't parts change. We proved it with our tool. So number one absolutely can be tested with a manometer to prove its authenticity. It can also be tested and proved with the power on using the hopscotch method. One land on the ground and the free hand coming into it and coming out of it. Do I have it there, and do I have it there? And we can also test a pressure switch through, is it open or closed, using continuity. Do we have a path, or is there not a path? Is there a beep or no beep? Moving on. Up next on our list is the rollout switches. Our 24 volts are coming into it and they're coming out of it. These are activated by when the flame rolls out. It gets too hot. And it's a resettable type deal. There's a little nipple on it. You can press it. It's a click and it closes. We don't like to do that. We want to test it right when you're there. Do you have 24 volts going to it? Do you have 24 volts coming past it? Or do you not? Or you could pull the leads off of it and you can test for continuity. Beep or no beep. Is there a path or is there not a path? I do want to remind when we are testing for continuity with the power off, we want to take the wires off of our component, off of our switch, and leave it naked and isolated. And that's how we really want to test for continuity. We don't want to risk any feedback coming from anywhere else in the system. We want to isolate the switch that we're testing. Number 3 is my high limit switch. This is a temperature sensitive switch, and it is found right inside of the heat exchanger. The whole purpose of this job is a safety feature. All of these are safeties. If something is stuck in the side of the heat exchanger, say homeowner wasn't running a filter and a piece of paper got shoved up in there and it's about to catch on fire, or a cat or an animal or something's going on in that heat exchanger. Or let's say we have a failed heat exchanger situation, rusted holes all through it. There's a lot of things that could be going on in the heat exchanger. So this safety is sat right in there on a temperature. Let's say the temperature is 180 degrees. If I am failing on that switch and I prove with my meter through continuity, right? I've put in the lead on continuity across the whole switch, one on one side here and one on the other side here. And I found that I did not have a path. I'm in a real no beep situation. I can't immediately fail the switch. I have to prove, is that switch lying, or is that truth, and is it indeed getting over 180 degrees? So in order to do this, the switch needs to close. Once the temperature has cooled down, that switch should close back up. We can prove this with the power off. The switch is isolated, continuity, ohms signal on our meter. We beep over to it, and there we go. Do we have a beep or do we not? Once it finally closes that path, we want to take a temp probe. We like the K-type temp probes that plug into our meters, and we can install a temp probe right in behind that high limit switch, screw the high limit back in, run sequence. When that high limit switch, if it trips again, we're going to be able to see exactly at what temperature did that happen, and you can prove a switch very fast. Did it open up at 120 degrees? If so, it's lying. That's a bad switch. It was rated for 180 or whatever the switch in question is rated for. So we need to keep an eye on that, and we can test it very easily just by running sequence. What temperature was there? If it did cut out at 180 degrees, now it's your job as a technician to find out, why is my heat exchanger getting this hot? Moving over into number 4, we see that we are at the thermal disc. This is located at the blower wheel. It also is temperature, and it also is individually based, so it says it right on it. At what temperature do I open, and at what temperature do I close? This can be tested with your hopscotching method with the unit on. You can have 24 volts coming to it. You don't have it coming out of it. It can be tested with the power off with continuity, using that ohm section again. Beep or no beep. Does it have a path or does it not? Is it giving you numbers or is it giving you OL? If it is open, the same thing. We need to let it close. We need to insert a temp probe in that area. We need to run sequence and see at what temperature did that thermal disc open, and is it indeed getting that temperature, and if so, why? Or is it a bad switch and it's lying? The last station on our roadmap is actually coming directly from the control board. This is the transformer feeds into the control board, and out of the control board feeds our control circuit. So we can see right here what are we actually getting from the board itself. We're getting that 24 volts somewhere in the ballpark of it, and that's what's supplying our control circuit. So far we've gone over how to hopscotch our way real fast through these things. We know that these switches aren't right next to each other in a beautiful circle. They're spread out throughout the gosh darn unit, and we got to find them, and we need to find them quick so before they close or they open on their own. So we want to prove our safeties and make sure that they're working like they're supposed to. Real quick, once again, we talked about safety number 1 was the pressure switch. We need a manometer. They're not very expensive. Get yourself one for $40-$50 and actually figure out what the pressure is. We've got number 2 for a rollout switch. This thing can be tested with a lighter. And is it going to trip the switch or is it not? What do we have here? Number 3, my high limit switch. That's another temperature sensitive switch. So it's tested through a temp probe. One of the ththings that I really love about a good furnace is it follows steps, it follows rules, and as a good tech, we can know our steps, and we can even break them kind of down into our own understanding so that you're paying attention. Step one, you're running sequence, so the thermostat calls for the heat. Then the induced draft motor turns on, the pressure switch is closed, the safeties prove themselves to be closed, then the gas valves open, then the igniter ignites, then the flame sensor proves it's got flame, and then the blower turns on. So it never changes these steps. If I'm getting all the way to my gas valve is open, I don't need to be looking at the pressure switch. Is it closing or not working? Is my thermostat not sending the right call? Is one of my safeties open? Well, they're all closed because the gas valve itself opened. You heard it. You saw that click. And you noticed to look beyond the gas valve. That's where you start. So what's that igniter looking like? How does it spark? And what's going on there? Moving into different types of gas valves, I drew this specific one to teach a technician who was working on an Armstrong unit, and his particular Armstrong furnace has this smart valve, which is this 4-pin prong connector. What's nice about these, doesn't matter what we're working on, there's a roadmap. Was able to look at this roadmap and see what each of those wires were. They're color-coded. Oh, well, looky here, these two are tied into that control circuit, and these two are pathed in from the board. So, we can tell real fast is your gas valve if all of a sudden you're losing flame after being running for 2.5 minutes, but all of the safeties are staying closed. You can go to this smart valve here and you can see that you can put a prong using hopscotch method, go to a ground and go right into pin number 2, and you can see it coming from the board, right, directly. And when you lost your flame, did you also lose 24 volts there? Or did the voltage stay and you still lost flame? And you can test all of your safeties real fast right at this particular gas valve, right off the 1 pin. It's going into the high limit switch, so it's right on that control circuit. So you can hopscotch right onto that pin right at the gas valve and watch all the safeties. Man, I lost flame and all of my safeties are closed. So this helps us as a technician not waste a lot of time scratching our head. I did add this induced draft motor to the board. A lot of times, we need to test it right there, and we can hopscotch the same way. One on the ground, one onto the power leg of that induced draft motor. It's only got 2 wires going to it. Do I have voltage or do I not? And if I have voltage right there at that pin, man, I do have 120 volts at there, and that motor's not coming on, that the motor's bad. Does that induced draft motor have a capacitor on it? If it does, you need to check that capacitor and make sure that it's still good. If it doesn't have a capacitor, the capacitor's good, I have voltage going to it, and the motor's still not turning on, we know that the motor's bad. If I don't have voltage there is no 120 volts. Well, then there's no reason the motor should be on anyways, right? Even though we're calling for heat, it's not getting the voltage. So our problem's before then, which is typically going to be like our control board area, whatever's sending the signal for the induced draft motor voltage to be present. That's going to be the next series of videos. We're going to be moving into the motor side of the house and how to test these motors and these control boards to see is the signal even going there, and how to take that into further depth. For those that made it this far, I did promise I was going to go over the top 5 things that I typically see when I'm out in the middle of these freezing cold situations, when I get a lot of no heat calls that come in. And if you're like me, then most likely when you're on your way to that call, you're going over your head. What kind of equipment does my customer have? Where is that equipment located at? Is that in an insulated space? And you're kind of troubleshooting. Before you even get there, you already have 2 or 3 different ideas of what you think might be the problem, and very fast ways to check these things so that you're not wasting the customer's time. You're in and off that job, and you're a professional and an expert at what you're doing. So typically when I'm having an emergency call coming from someone, it's safe to assume that they're not a PM customer of anybody's, definitely not of yours, because you would have most likely caught this problem during a service call. So I'm typically coming into units that have never been serviced in 20 years, 15, 10, it's been a long time. And that first number 1 call is the flame sensor wins. Congratulations, dirty flame sensor. I see this by running sequence when I get onto a unit, and and I'm looking at it and I'm watching it go through the sequences. Gas valve opens. I'm watching the flame come on. The flame's only on for like 15, 20 seconds, and then bada bing, bob, boom, I lose flame. And I'm in a whole recite, and then it just does the whole thing over again. We can pull that flame sensor out. It's typically a 1/4-inch screw. Pull that flame sensor out and clean that thing. Use an emery cloth. And I know the gangsters like to use the dollar bill. I know men like to use a $100 bill to clean it. Whatever. Emery cloth it up. Get it clean. Plug it back in. And once that flame sensor proves that it has a signal, the flame's going to stay on for you. Number 2 dirty reason, drum roll please, that's right, it's going to be dirty filters. And we're going to go a little farther, not only dirty filters that nobody's changed in 10 years, but dirty coils. Oh yes, dirty coils that are so caked up from years of neglect, from not being on a PM service of any nature, and it's just not allowing that air to pass. The same as dirty motors. I'm going ahead of myself. Just dirty in general really causes the number 1 cause of problems that I see. I should have put it as number 1 instead of the flame sensor. It's definitely dirtiness, and not in like a nasty kind of way, just a filthy unit that can't breathe, can't pass the correct amount of airflow across those coils as it needs to, and it's high limited out in a lot of situations. I could even carry on preaching just a little bit more about dirtiness to look at the fins, look at the veins inside of the blower wheel itself, and run your finger through that thing with the power off. And are you pulling up an entire 6 inches of dust and stuff out of the insides of those blower wheels? Because if you are, you're not passing the right amount of CFM across that heat exchanger. Could be why your exchanger's getting too hot, why your motor's getting too hot. So dirtiness really is a high-end call. We get those all the time. Take the time out when you're inspecting those coils. What direction does the air flow? Okay, what direction does the air flow? I don't know how many times I've been the second or third company called out to a location on a high limit situation where they're failing heat exchangers, and you get in and look out and find that the inside of the evaporator coil, where the air passes through, follow the current from the blower through the heat exchanger into the evaporator coil, and we're going to see it's caked up in there. It's not passing any, no air's passing through there. So cleanliness is just so important on these units to let them perform well and to get longevity out of our equipment. The third most popular reason that I'm on an 80% furnace emergency down call in the middle of wintertime is a broken igniter. My gas valve is opening, but my flame's never kicking on. My glow plug's never glowing up. It's never making it there. That's a visible thing. We're going to see that igniter is broken. There is an ohm value that we can test on that with our meters and look at the paperwork per igniter, and you can see the ohm value. And, is it in the ballpark or is it not? Typically what we're seeing here is a broken igniter, or it's not a broken igniter. A bad one, it's getting signal or it's not. Is it getting the voltage and not igniting, or is it not getting the voltage? We're back to that same type of situation. The number 4 most popular reason that I end up at somebody's house in their attic or in their crawl space looking at a unit in the middle of a winter storm is going to be motor failure. These are blower motors. And, we could preach on these blower motors of why they're failures. Are they really the problems of the manufacturers? Or are they problems from not being serviced or being improperly installed at the beginning? Because I've seen motors fail for a lot of reasons. Some of those reasons a motor fails a bad capacitor, so we need to look at those. We're back at capacitors again. Go check the capacitor that feeds that motor and make sure that it's within 6% of tolerance of what it's rated for. If it's not, change it out and see if that fixes your problems. Motors could be failing because they're getting too hot. Why are they getting too hot? Are they dirty, like we mentioned before with number 2? Right? Is the motor itself just caked with dirt and it can't breathe and it's naturally getting too hot? We need to clean that motor off and let those thermal limits inside of the motor, let those close. We can test those with our meter. Beep or no beep, right? Is it open or is it closed on those windings? And motor failures, are they too hot to touch? Put your hand on it. Is it singeing hot? If it is, that's too hot. That could be bearing play. We get into how do we really test that motor? Does it have voltage going to it, and is it turned on? Or does it not? If the voltage is there and the motor's not on, that's a bad motor. Typically, if the voltage is there and the motor's not on, we can hear that and see it binded up. It's just locked up. But if the voltage is not there, well, then we should not have that blower motor on. That's not your problem. We need to go back to the highway and see what's telling the blower motor to turn on or off, and why is it not sending the signal. These are our top ones. I think we have one more left that I promised you, because I always just give entirely too much. The number 5 reason that I'm usually on a down call in the middle of a winter storm are these 90% furnaces. Okay, we're not going to spend a lot of time talking about them, but it's 90% furnaces. How can I tell, is my furnace an 80% furnace, or is my furnace a 90% furnace, Mr. Service Tech? Well, do you have a metal flue pipe coming out of there? Do you got some PVC pipes coming out of there? All 90% efficient furnaces have 2-inch PVC pipes for their intake coming in and out of them, and these things make water, unlike our 80% furnaces. They don't make no water, right? They just make flue gas, and that gas goes out the roof. Well, when I have a unit like a 90% furnace, these new fancy things that are in especially new house builds, new construction builds, because they're not built like they were in the old days, I'm seeing units installed in uninsulated spaces. So when the area that my unit's in is in 10 degree weather, well, what happens at below 32 degrees when water's present? Right? It turns into ice. I see a lot of those collector boxes have been frozen. Not only been frozen, but they've expanded under the ice and now have cracked the collector box. If that's left unattended, within a couple years, that unit's going to look horrible. Run every gasket from here to there on it. So, I've seen P-traps frozen solid because they're in uninsulated spaces. We can fix that situation kind of temporarily and probably permanently by grabbing some of that heat wrap tape. It needs a power source. You can plug it in, wire it right into the unit, and you can wrap that condensate up with that to allow that unit to stop itself from freezing. I believe I gave the top 5 reasons why I'm typically on a down call in the middle of a winter storm. I hope I helped somebody out of a difficult situation, or help expand it or inspire it a little bit more to be a better tech, to grab our tools when we're teching, stop Googling some things, stop hitting the service desk, and start looking at the basics of some stuff. Do I know the furnace steps of operations? Do I have a voltmeter? Do I have a manometer? Do I know what I'm testing for? And do I know how to prove it or disprove it? Once we can get rid of the scariness that there's 6,000 wires here, and we can really get down to the brass tacks that there's 12 components here, we can really start to speed up our service calls. We can make educated diagnostics and be able to prove that in a court of law if you needed me to, of why you failed that pressure switch. Well, I'll tell you exactly why, and here's a picture of it right here on my meter. This is what it was doing. We can prove our work. I hope you guys enjoyed today's training session. I've been doing a lot of training modules lately, and I just really enjoy teaching. I prefer it in person, but this is kind of a scratch the surface session. Let's see how it does, and hopefully I can come back in here with my second video, which will get us into testing control boards and thermostats and motors. You guys be good, or you be really good at it.